Okay, everyone. Today our question is going to be an induction question. It's an 8 marker, so you guys want to get this correct. And it's going to be a divisibility induction question. So our induction question here is n times bracket n squared plus 5 is divisible by 6 for all positive integers. So first, we should write let Pn be the statement. So let Pn be the actual proposition. And just copy this right down here. Okay, so first we consider a base case. Base case. And since this is for all positive integers, it's P1. So what you do is you sub 1 into this, your proposition. You get 1 and 1 plus 6. 1 plus 5, 1 plus 5, mind that. And this is equal to 6. And 6 is divisible by 6. And thus we have to write this. You have to write this down. Thus base case holds true. Okay, so next, we want to prove that for the n plus 1 case. So
assume that P of K is true.
yeah. So we want to show that n plus 1 squared plus 5 is divisible by 6. Note this notation. And what we do is we first assume that the proposition holds for any integer p of k. So assume pk holds. Now we consider pk plus 1. Okay, so what we do now is we essentially just sub in k plus 1 for all these, for all the n's here. So basically look like this, but with just k's. So what we do is k plus 1, and then bracket k plus 1 squared plus 5. Note that you have to square the whole n, so it should be k plus 1 squared, like here. So we want to show that this is divisible by 6. First, we want to expand this. What is this equal to? It's equal to k plus 1, k squared plus 2k plus, that's a 1, so that's 1 plus 5, so that's a 6. And yeah, it's multiplied by k plus 1. Let's multiply this out again. It should be k cubed plus 2k squared plus 6k plus k squared plus 2k plus 6. Okay, now that we have this here, a trick for divisibility induction questions is that we always want to use our induction hypothesis, which is that our proposition holds for the case p of k. So what we want to do is basically we want to try find the induction hypothesis within this bunch of values. So note that in the induction hypothesis we have k squared, and plus 5, right? So essentially we match this up. K squared plus 5. So what this actually is k cubed plus 5k. So how do we get this value? What other values we have to add so that it's equal to the above equation? Well, note that if you simplify this, this is k cubed plus 3k squared plus 8k plus 6. So we have a k cubed plus 5k here. What else we need to add on? We want another 3k. We want another 3k squared. And we want another 6. So at this point, in our induction hypothesis, we assume that this holds true, that this is divisible by 6. So what you have to do now, since these are just sums, right? If you show that this is divisible by 6, then this whole expression is also divisible by 6. So let's raise the thing up here. So, okay, let me just copy this up. k squared plus 5 plus 3, and let me just factorize it right now. See k squared from here plus k plus 2. Okay, so like I said before, by induction hypothesis, this is divisible by 6. Now we want to show that this is divisible by 6, so that the whole expression is divisible by 6. And since this is also divisible by 3, we just want to show that this is divisible by 2, right? Because 3 times 2 equals 6, and thus it will be a factor of 6. So, and divisible by 6, sorry. How do you show that this is divisible by 2? Let's consider this then. What we do is, we factor k squared plus k, factor this, to k and k plus 1, plus 2. So what we have now is, this is divisible by 3. This is an odd times an even, and that's an even. An even number add plus 2 is also even. So this will be a multiple of 2. And thus this whole expression here will be a factor of 6. And because this is a factor of 6, then the whole thing is going to be a factor of 6. Okay, I guess you can write this down in words in your actual exam. And we're not quite done yet. All we have to do now is write our conclusion. So in our conclusion, I guess you would write something similar to like how this would work out. And essentially for just like the typical conclusion, what we write is, since P1 is true and PK plus 1 holds true when Pn is true, PK, that's my bad, PK is true, and thus Pn is true for all n, and note the domain, positive integers, and we're done. So this was an 8-mark question. It's a relatively hard induction problem, especially this step, but we believe you that you'll get it, and hope you learned something new today. Thank you.